Hey, welcome. Today, we are diving into one of the coolest tools in all of engineering and applied math. Seriously, it's a technique that takes these ridiculously hard problems and makes them so simple you could have probably solved them back in high school. Sounds a little like magic, right? Well, it is, but it's the magic of mathematics. So let me just start by asking you this. No, really think about that for a second. What if you could take a nasty calculus problem, kind of wave a magic wand over it, and have it just rearrange itself into a simple algebra equation? Well, that's not fantasy. That's exactly what the Laplace transform does. And today, we're going to see precisely how it pulls it off. All right, so first, let's set the stage a little. Why do we even need a tool like this in the first place? Well, the answer is something called differential equations. They're basically the language that we use to describe our changing world. I mean, everything. The way a bridge vibrates, how current zips through a circuit, even how populations grow. All of that is modeled with differential equations. They're absolutely crucial. The only tiny problem? They can be a complete nightmare to solve. The calculus can get really messy really fast. So if trying to solve the problem head-on is just too hard, what do? Well, you don't go forward. You go sideways. You literally take the problem out of its home turf and move it somewhere else, a place where the rules are way, way simpler. That's the whole idea behind a mathematical transform. And the Laplace transform, that's our portal. It's our doorway to this simpler world. It takes a function that's all about time, we call that the t domain, and it flips it into a new function that's all about frequency, or the s domain. You can just think of S as this new variable in a parallel universe, a universe where the math suddenly becomes a whole lot easier. And here is the entire three-step magic trick. It's actually this simple. 1, we shove our difficult calculus problem through the portal into the easy S domain. 2, while we're there, we solve it using just basic algebra. And 3, we pull our simple answer back through the portal and boom, the solution to our original really hard problem is sitting right there. Okay, so you're probably wondering, how on earth does that actually work? What is the secret sauce that makes this transfers domain so much easier? Well, it all comes down to how this transform deals with the single hardest part of any differential equation. This is it. This is the whole ballgame right here. That super complicated, messy calculus operation, finding a derivative, it gets turned into simple multiplication by our new variable s. That one move completely changes the game from calculus to plain old algebra. And this right here, this is the magic spell. This one little equation is the key that unlocks everything. It's what turns the calculus into algebra. Let's break down what it's actually telling us. Okay, don't let the letters scare you. On the left, you've got the transform of the derivative. That's the calculus part we're trying to get away from. But look what it becomes on the right. You've got the transform of the original function, f of s, and it's just being multiplied by s. Then all you do is subtract f of 0, which is just the starting value of your system, and poof, just like that, the calculus is gone. All right, theory is one thing, but let's see how this incredible trick actually works in practice. We're going to take a real differential equation and solve it, right here, step by step. So here's our challenger. It's what's known as an initial value problem. We have our differential equation, and we also know where our function y starts at time 0. Now, without Laplace, this would take some real work. But with it, you're going to see it's a piece of cake. Okay, first things first, we take the Laplace transform of every single piece of this equation. We're not solving anything yet. All we're doing is moving the whole problem into our new, much friendlier world. And would you look at that? The calculus just vanished. Using our secret formula, that y prime derivative became sy of s minus 1. The other parts, the y and the exponential term, we just look those up on a standard table of transforms. The main thing to see here is there are no more derivatives. This is just algebra now. And now for the easy part. Seriously, we're in the S domain, and all we have to do is what we learned in high school. We just need to shuffle things around to get that y of s term all by itself. So after we factor out y of s and move a few things around, we get this. Now, this is our solution, but remember, it's still in the S domain. It's like we have the answer in another language. So now we've got to get it ready for the journey back home. To make that trip back to the time domain as easy as possible, we have to break this complicated fraction down into simpler pieces. It's a pretty standard algebra tool called partial fraction decomposition. It basically just turns one big, ugly fraction into a couple of small, simple ones. And once we do that, our y of s solution looks like this, these two really simple terms. Now, each one of these is a super common form that you can find on any inverse Laplace transform table. They're like perfect, clean passport stamps for our trip back to the real world. We're on the home stretch. This is the final step. We take our simplified expression and we use the inverse Laplace transform. We are pulling our answer back through the portal, out of the frequency world and back into the world of time. And there it is, the final answer to our tough calculus problem, found almost entirely using algebra. How cool is that? We literally jumped to another dimension, solved it easily there, and jumped back with a solution. It's an incredibly elegant way to solve a problem. So, okay, besides just being a really neat math trick, why is this so important? Why is this one of the absolute cornerstones of modern engineering and physics? Let's just quickly recap the big wins here. First, and most obviously, it turns hard calculus into easy algebra. Second, it automatically takes care of the starting conditions for you. Remember how that y of 0 equals 1 was just built right into our first step? And finally, it gives us a powerful, repeatable recipe for solving a massive class of real-world problems. And that kind of leaves us with a bigger thought, doesn't it? The Laplace transform teaches a lesson that goes way beyond just math. Sometimes the best way to solve a really hard problem isn't to just attack it head-on with brute force, but to step back and find a completely different way to look at it. Thanks for watching.